Okay, so today we're going to look at a few different type of matrices that we can use in different scenarios. So the first one we're going to look at is a binary matrix, and all we mainly need to know is a binary matrix is only got ones and zeros. Used a lot in, I believe, computer coding. We only use ones and zeros. So you can see there, that's what a binary matrix is. So then it leads us into a permutation matrix, which is a permutation is a binary matrix, so therefore it only has ones and zeros, but it is a square binary matrix, so that's important. So a permutation is a square, and a permutation can help rearrange the elements of another matrix. And we saw this, we can see, yes, in the last chapter when we multiplied a matrix, we were using it to sort of increase the prices. So this way, what this permutation matrix is going to do is going to rearrange the elements. So if we have a look, we've got an example here. So we have this matrix here, and it has letters. So it doesn't matter, remember I said it doesn't matter, your matrix can have elements of letters. So this is a 3 by 1. And we're going to multiply it, and we're going to pre-multiply, multiply in the front of it with this 3 by 3 permutation matrix. So you can see it only has ones and zeros. So when you do this, obviously we've got it down here, they're going to multiply this permutation by this other matrix X. So if we were doing our first so we'll just check it. So if we checked it, we've got a 3 by 3 with a 3 by 1. So it is defined, and our answer will be a 3 by 1. So if we were doing that first column, the first answer here, the rat, what it would be, it'd be this row by that column. So you can see when you go 0 times t is 0, plus 0 times a, which is 0, and then you've got the 1 times r. So that makes the r show, because 1 times r is r. And that's how it shows. So you can see by multiplying it, originally we had the TAR written downwards, and now when we multiplied it by this permutation matrix, it rearranged those letters, and now we've got RAT down there. Okay, if you square the permutation matrix, so you can see, and then times it, so we can do that because it's a square matrix, so we can raise that permutation matrix to the power of 2. What we're going to do, it's going to do it twice. So it's rearranging the letters, and then it rearranges it again. So you can see though, when we did that, it went back to the start. So sometimes they might ask you, how many times are you going to multiply before you're back to the start? Okay, so you just keep changing the power on your matrix, and then whatever number you get up to. You'll see there's a question like that in there. So, and they just brought up an example that, this down here, that P2 was an identity matrix, just because the one's down there like that. Okay, so let's have a look at this exam question using permutation. So you don't really get asked to define it, you just get asked to use it. So here, it says the matrix product is equal to, so obviously understanding how the manual multiplication works, it can make it a lot easier because you're not going to want to type in that 5 by 5. That's going to be annoying and time consuming. So we're going to do this. We can see we've got a 5 by 5 with a 5 by 1, and we'd end up with a 5 by 1. So if we do the first row, and we'd go like this, you can see down here, you can see that there's only a 1 on that fourth number, so that means that fourth number down is going to show. So I would then get a P in my answer. So then if I do the next one, so if I went row and I go down here, see where I'll just rub that out. See where the 1 is on the third number? So on the third letter down will be what appears, which is an A. So then I have A, so then I'd have A. So what about this third line? If I was going across here, which letter's going to show? Where's the 1? Yeah, good. So L will show here. And then the next one, which we've got it on the second, so the second letter will show. And then the last one, we've got a 1 on the last one, so the last letter is going to show. So we just had to look for that answer, which is it D? Yeah, D. Okay, matrix P is a 4x4 permutation matrix. Matrix W is another matrix such that the matrix product PW is defined. So the matrix product that results in the entire first and third rows of W being swapped in the permutation being swapped. So they want the permutation. So it's a bit confusing, so we're just going to write out what they're doing. So they're doing P.W, and you know permutation is a 4x4. So here, just do like what we've done in our examples. We've had we're just going to make it a 4x1, yeah? So we just make a 4x1, and I'm just going to make up a W matrix, and I'm just going to I'll just put any letters. I'm making up any letters here. So maybe I'll just write A, B, C, D, okay? So what's going to happen, we're going to multiply the permutation first, and so we're going to multiply the permutation here, and what we're going to get with this W, and we're going to get our answer. And what we want, they said they want the first and third rows to be swapped. So that means I want to see C here and A there. Does that make sense? So I've swapped the first and the third. That's me swapping. So when we run along, if we were doing, say, the first one, for example, I want C to show. So if I was running along here, and remember I'm going to dive down there, so where do I need the 1? I need the 1 on the third one. So which one has a 1 on the third one? B. So that's already my answer, yeah? So hopefully it would work. Does it bring a B in the second answer? It does, doesn't it? Yes? So B is the second. And in the third row, I want to see A show, which I do. It's got a 1 on the first one. And in the last one, I want to see D show, so the 1's on the D. Okay? Does that make sense? Yeah. Okay, so this now that was permutation. Now we're moving into another one, is a communication matrix. So a communication matrix is also a square binary matrix. So remember, square and binary means only 1s and 0s in the matrix, okay? So, and it says where 1 in a communication, where 1 represents a link in a communication system. So a communication network contains a set of people where they can have a one-way or two-way communication link. A two-way communication link could be via a phone. So communications matrices can be set up from communication networks. So this diagram here is a communication network. Okay, so you don't need to, obviously you never have to define anything, but if they talk about a network in the question, they're talking about the dots and the lines. That's what they're talking about. So what we do is we can set up a communication matrix that explains how these people communicate with each other. So what we do is, if we were trying to set this up, you look at, first of all, how many people you've got. So you've got 4 people, or 4 things. It means you're going to have a 4x4. And just to make it easier, I'm just going to call them the people. So there's Eric, Brianna, Daniel, and Catherine. And I'm going to go the same, and see how I'll change it around because they've done it in their example. They put Catherine first. They're just doing alphabetical order. It wouldn't make a difference as long as you follow your communication matrix. All right, so what we're saying is, if you can talk directly to the person, so if there's an arrow or a line that's linking you together, so say, for example, Eric and Brianna, they can both talk to each other, like they can communicate. So what we're going to see is, we'll see a number 1 between A and B. Okay, so there's the number 1, and we'll also see it between B and A. So we don't really have anyone, Arik's not going to talk to himself, so this A and A would be 0. Now, can Arik talk to Catherine? Yeah, there's an arrow going down, so I say yes. And can Arik talk to Daniel? Yes, I'm going to put a 1 there. All right, let's go check with Brianna. Now, can Brianna, she's not going to talk to herself, so we'll see a 0. Can Brianna talk to Catherine? Yes, the arrows are going both ways there. And can Brianna talk to Daniel? No. All right, because the arrow's not going that way. Okay, so now we're on to Catherine. Can Catherine talk to Arik? No. The arrow's not going that way, is it? Can Catherine talk to Brianna? Yes. Catherine doesn't talk to herself, and Catherine can talk to Daniel. Okay, and then the last one, Daniel does not talk to Arik, it only communicates there. He can talk to Brianna, can't talk to Catherine, and doesn't talk to himself. All right, so there was a way, that's how they got this one. And they're saying from to. So that's what we were doing. We're going from this person, from this side, and we're saying talking to that person there on that side. Okay, so we're going to practice that. That's called, this is called one-step communication, when the directly who's talking to them. So we'll have a look at that. Okay, so from this communication matrix, we're able to see who can directly talk to each other. So when you directly talk to each other, that's like a 1-step. So you might want to call that 1-step communication, because that's how we refer to that. Okay, so if you can directly talk to the person, no Chinese whispers, just directly talk to them, that's 1-step communication. And we can see from the network diagram that Brianna cannot communicate directly with Daniel. However, Brianna can communicate with Daniel by sending a message via Catherine. So here where they talk about this, Brianna can communicate with Daniel by sending a message to Catherine. So Brianna could go like this. She's going to send that message and go like that. Can you see that is a 2-step communication? It took me 2 steps to get my message from the one thing. So that's 2-step communication. That's what that means when you use someone else to get the message to the next person. Okay, so you can, the power of the matrix representation in the squaring of the communication matrix. So the way you can find, so here we've got setup. They found this was our first communication one. So we might want to write this was 1-step communication here. Okay? And what they do, they're showing you if you square that, which means you multiply it by itself, you get this, obviously this matrix here would be C squared. Okay, and what that matrix is the matrix that shows, this shows the number of 2.
Improve your user interface.
Okay, so this shows the number of 2-step communications. Okay, so if we looked at Brianna up there, I'm just going to go back to our Brianna up there. So she got a message to Daniel via Catherine. She can also get one by going Arik to Daniel. Can you see that as well? Yeah, that would be another 2-step. So is there any other options that Brianna can get a message to Daniel via 2 steps? No? So I'm going to write it. So we've got here, if we had the 2-step options for, I'm just going to say Brianna to Daniel, we're going to have one option was we went Brianna, Catherine, Daniel. The second option was we went Brianna, Arik, Daniel. So there's only 2 possibilities. So you should see over here, down the bottom in our 2-step, where we have Brianna going to Daniel. So if you go along the B and go to D, can you see there's a 2? And that's those 2 options. So the two-step communication is telling you how many options there are, okay? And we saw there was only 2 options for that combination where I want to go from Brianna to Daniel. So you see the 2 there. That's what that 2 indicates, okay? Okay, so we said that if we square our original communication matrix, we get the 2-step communication matrix. So down here, this is our C squared from our scenario. So this is showing the 2-step communication. So it's going through it here with you in the notes, what I've just done. So the number in red indicates there's 2 different ways from Brianna can communicate with Daniel, and then they've written them out. So there's our 2 options. So you might go, this is option 1 and option 2, okay? And then the blue, the number 1 highlighted in blue indicates there's 1 way that Catherine can communicate with Eric via someone else. And so there's that 1 option here for that scenario. Now, with the green, when they've highlighted this leading diagonal, what that one's called in a communication matrix is it's known as a redundant communication link. Why is it redundant? Because that's the message you're sending back to the same person. So why would we ever want to do that? The thing sending it out, because it's not always people, it can be machines, yeah? A machine's communicating with another machine. So the machine already knows what it's doing, it doesn't need the same message back, all right? So that, or, communicating, so that's called a redundant link. We're just rehashing here. So a redundant communication is a communication link is said to be redundant if the sender and the receiver are the same person. So you end up at the same spot. Now, often they will ask, now this is being careful, when they ask what is the total number of 1 and 2-step links. So this word "and" there means that you're gonna add them together. So when they want the total 1-step and 2-step communication links, is you simply add the 2 matrices together. So this would have been your original communication matrix, and then you add it with your one that you squared, and you end up with this one. So this is the sum of C and C squared. So when you're trying to add up the numbers, all you do is you can add across. So when they say what is the total number of 1 and 2 steps, for A, you're just going to add across here. So you'd go 4, so what's that? 1 plus 3 is 4, plus 2 is 6, plus 2 is 8. So this one's 8, this one has 7, this one has 5, and this one has 3. So these are the total number of 1 and 2-step communications. So they may ask that. Just be very careful if they're asking for both 1 and 2. That means you add them together. If they're just asking for 2, just add up the 2 rows and things like that. Okay, so Eva, Wong, Yummy and Kim are students who are staying in a backpackers hostel. Because they speak different languages, they can have problems communicating. The situation they have to deal with is Eva speaks English only, Yummy speaks Japanese only, Kim speaks Korean only, and Wong speaks English, Japanese, and Korean. Conveniently, this information can be summarized in a network diagram as shown above. In the diagram, the arrow linking Eva and Wong indicates that they can communicate directly with each other. So that can directly is 1-step communication, and they both speak English. So they want us to construct a communication matrix. So we often call them C, so I'm going to call it C. And what we'll do is we've got 4 people So we're going to have a 4 by 4. So we're going to have, I'll just do Eva, Wong, Yummy, and Kim. It doesn't matter how you put them in, but see, if I've done that order down that way, that order, Eva, Wong, Yummy, and Kim, has to go the same way across the top. So we're going to say they can from here to there. So they're going to speak from there to there. So Eva to Eva's not going to talk to herself. But can Eva talk to Wong? Yes. So there's a 1. Can she directly talk to Yummy? No. And she can't directly talk to Kim either. So now we look at Wong. Can Wong talk to Eva? Yes. Wong doesn't talk to themselves. And can Wong talk to Yummy? Yes. And they can also talk to Kim. Okay, Yummy and Eva, no. Yummy and Wong, yes. Yummy to Yummy, no. And Yummy to Kim, no. Kim to Eva, no. Kim to Wong, yes. Kim to Yummy, no. And Kim to Kim, no. So here you've got your communication matrix. So you can see on the redundant link, on our redundant link, we have zeros. Which makes sense, yeah? Because why would they talk to themselves? Okay, so this is one-step communication. If you had to get 2 steps, just to help you, so if you had to get 2 steps, what you're going to do is you're going to type that matrix into the calculator, this first one, and you're going to raise it to the power of 2, okay? So you just would do that and you'll get your answer, okay? So that's how you would do, and that's how you get C squared and you get your 2-step communication matrix.